In physics, there is a hard boundary on reality, the speed of light. For decades, scientists accepted that nothing could ever travel faster than this universal speed limit. To see why, imagine if the sun suddenly vanished. Isaac Newton argued that gravity acts instantly across any distance, meaning Earth would immediately fly off into space. But Albert Einstein realized gravity is caused by the bending of spacetime. If the sun disappeared, a ripple of gravity would spread outward, taking 8 minutes to reach us. If gravity was instant, an observer flying past us at a high speed would see something impossible. Due to the way relativity distorts time, they would actually see the Earth fly off before the sun even disappeared. The effect would precede the cause. To avoid that kind of logical disaster, effects must spread from place to place at a finite speed. Physics demands a local universe, where nothing influences anything else without a measurable delay. But quantum mechanics threatened to break that rule. The new theory stated that a particle's location is described by a wave of probabilities spread across space. When you measure that particle at a specific spot, the entire rest of the wave must collapse to zero everywhere else in the universe, instantly. In 1935, Einstein and his colleagues devised a thought experiment to expose how absurd this was. They imagined two particles whose properties, like spin, are linked to conserve energy. When the particles are separated by vast distances, measuring one to have a positive spin forces the other to instantly take on a negative spin. To Einstein, this apparent instant communication meant quantum theory was incomplete. He argued the particles weren't sending signals faster than light. Instead, they must have carried a pre-agreed plan, like sealed envelopes containing hidden instructions, determined while they were still together. Niels Bohr, the leading voice of quantum mechanics, dismissed the criticism. He argued it was meaningless to ask what particles were doing when unmeasured. The math accurately predicted laboratory results, and to Bohr, that was all physics should care about. Because both the quantum wave collapse and Einstein's hidden instructions made the exact same predictions, there was no way to run a test. The true nature of reality was trapped in a purely philosophical debate for decades. Then, in 1964, a physicist named John Bell realized the debate could be settled. He discovered a way to transform Einstein's thought experiment into a rigorous mathematical puzzle. By this time, technology had caught up. Scientists could reliably generate pairs of entangled particles and send them into two independent measuring devices. On the exact same axis, detectors always measure the opposite spin, 1 plus, 1 minus. But Bell's innovation gave experimenters a choice, independently rotating their detectors to 3 different angles, 0, 120, and 240 degrees. This multi-axis setup created a strict logical trap. It forced the two competing theories to make completely different predictions about how often the two detectors would disagree with each other. According to quantum mechanics, instant collapse dictates the particles will disagree exactly 25% of the time. But if Einstein's hidden instructions were right, calculating every possible strategy reveals they must disagree at least 33% of the time. That 8% difference was all that was needed. It provided a clear, measurable boundary to finally determine if the universe allows instant communication. In the decades that followed, experimentalists like Elaine Aspect built highly sophisticated optical setups to execute Bell's test, tracking the collision of millions of photons. When the final counts were tallied, the disagreement rate was precisely 25%. The results perfectly matched the quantum mechanical prediction. Because the rate fell strictly below the 33% minimum required for local hidden variables, the logic is inescapable. Particles do not carry pre-agreed plans. John Bell's proof established a new, uncomfortable fact. Any theory that correctly describes our universe must be non-local. What Einstein famously called spooky action at a distance is a genuine feature of reality. Information about that collapse spreads across vast distances instantaneously. The only reason this doesn't shatter the core logic of general relativity is that quantum measurements are inherently random. Because you cannot control whether you get a plus or a minus, you cannot harness this instant connection to send a coded message or reverse cause and effect. It is an uneasy truce. The mechanics may prevent actual faster-than-light messaging, but the universe operates in direct conflict with the spirit of Einstein's relativity. Yet there is a single loophole that can save Einstein's dream of a completely local reality. The entire paradox hinges on the assumption that a particle's wave function collapses. The many worlds interpretation proposes that collapse never happens at all. Instead of forcing one result, all possible outcomes occur simultaneously. You, the observer, become entangled with the particle, and the timeline splits. If true, the distant particle never communicates faster than light. Both answers exist in parallel realities, so each version of you encounters the matching particle. Accepting this resolves the paradox, but at a massive conceptual cost. It means every single quantum interaction infinitely fractures our reality, generating countless parallel universes where absolutely every probability plays out. Ultimately, Bell's test forces a choice between two radical descriptions of reality. We must accept either that particles coordinate across the cosmos faster than light, or that our universe is endlessly branching into parallel worlds.